Four men walk across a sun-bleached courtyard toward the cafeteria. Enrico Fermi moves among them, hands clasped behind his back, eyes distant. These are not ordinary men. These are the physicists who split the atom, who turned sand into glass at Trinity, who rewrote the rules of reality itself. Inside, they collect their trays.
This project
The
timeline is
conversation
aggressive.
drifts,
We'll need
as
to
it often
prioritize the
does
specs.
among brilliant
Agreed.
minds,
The client expects
seeking
results. Let's
refuge
review
from
after
white
lunch.
comic books,
What?
flying
He
saucers,
said the deal is
morning's
off.
newspaper.
Off. That's
Someone
impossible.
mentions
This
the recent
changes
UFO
everything.
reports.
We have to act
Laughter,
now.
skepticism, the comfortable rhythm of rational men dismissing the irrational. They sit, they eat, and then Fermi stops fork halfway to his mouth. Where is everybody? The table goes quiet. The question hangs in the air like smoke. His colleagues look at each other. Nobody understands what he's asking. Where is who? What are you talking about, Enrico? But Fermi isn't talking about lunch companions or missing colleagues. He's talking about something else entirely. In 3 words, he has opened the largest mystery in modern science. And 74 years later, we still don't have an answer. Let me show you what he saw. Fermi was a calculator. Not in the metaphorical sense, he actually calculated constantly, compulsively, turning every question into numbers. How many piano tuners in Chicago? How much energy in a nuclear explosion? His friends called them Fermi problems, back-of-the-envelope calculations that captured the essence of reality through pure mathematics. That day at lunch, he did what he always did. He calculated. The Milky Way galaxy contains 400 billion stars. 400 billion. Write it out, 4 followed by 11 zeros. 400,000 million suns scattered across 100,000 light-years of space. Take a breath. Feel that number. Now, current estimates suggest 20% of those stars host planets in the habitable zone, the narrow band of distance where liquid water can exist on a surface. 20% of 400 billion equals 80 billion potentially habitable worlds. 80 billion chances for life. But let's be conservative. Let's assume life is rare. Say only 1/10 of 1% of those habitable planets actually develop life. That's still 80 million worlds with biology. Go further. Say intelligence is even rarer. Only 1/10 of 1% of life-bearing worlds develop technological civilization. That leaves us with 80,000 civilizations in our galaxy alone. 80,000 species who built telescopes, who split atoms, who looked up at the stars and wondered. Fermi did this math on a napkin. Probably took him 30 seconds. And then came the question that would haunt us for 3/4 of a century. If the numbers say the galaxy should be teeming with intelligent life, if 80,000 civilizations should exist just in our neighborhood of the universe, if some of them should be millions or even billions of years older than us, where is everybody? Why is the sky silent? The math gets worse when you add time. The universe is 13.8 billion years old. We know this with extraordinary precision. Our margin of error is roughly 40 million years, which sounds enormous until you realize it represents only 0.3% of 1% uncertainty. We know the age of the cosmos more accurately than we know the age of most mountains on Earth. Earth formed 4.5 billion years ago, young cosmically speaking. For 9.3 billion years before our planet even existed, stars were forming, planets were coalescing, and the conditions necessary for life were emerging throughout the universe. 9 billion years of opportunity. Life appeared on Earth within the first billion years after our planet's formation. Fast. Almost suspiciously fast. The moment conditions allowed it, chemistry became biology. If this speed is typical, if life emerges quickly when conditions are right, then the universe has had 9 billion years head start on us. Consider what that means. If a civilization formed just 1 billion years before Earth, they had a billion-year advantage in technological development. 1 billion years. Humans went from chipping stones to landing on the moon in 3 million years. What could a species accomplish with 1 billion? They should be everywhere. Their signals should saturate the sky. Their megastructures should be visible from across the galaxy. Their probes should have mapped every star system, including ours, millions of years before the first human ever looked up and wondered what those lights in the sky might be. And yet, silence. Perfect, absolute cosmic silence. This isn't just the absence of radio signals. This is the absence of everything. No obvious megastructures harvesting the energy of entire stars. No atmospheric signatures showing industrial chemistry on distant worlds. No unexplainable dimming patterns in stellar light curves. No one answering our calls, no one visiting, no one leaving markers that scream, intelligence was here. The sky is not quiet. The sky is mute. And that should terrify us, or at least make us think very, very carefully. Let me take you back further to understand why silence wasn't always expected. The search for extraterrestrial intelligence. SETI began in earnest on April 8, 1960. A young astronomer named Frank Drake pointed the 85-foot radio telescope at Green Bank Observatory toward two nearby stars, Tau Ceti and Epsilon Eridani, both sun-like, both potentially harboring planets, both close enough 11 and 10 light-years respectively that any radio leakage from a technological civilization might be detectable. Drake was 30 years old. Brilliant, methodical, and filled with what can only be called hope. Not naive hope, scientific hope, grounded in probability and mathematics. He called the project Ozma after the princess of L. Frank Baum's Oz, a place that was strange and wonderful and just beyond reach. For 150 hours, Drake listened. The telescope swept across those two stars, collecting electromagnetic whispers from the void. Every frequency analyzed, every anomaly investigated. The team worked in shifts, monitoring the data in real time, ready for that moment, when the random hiss of cosmic static would suddenly organize into pattern, into meaning, into proof. 150 hours. Nothing. Not a whisper, not a hint. Just the eternal background radiation of the universe. The random noise of hydrogen clouds and distant quasars. The meaningless static of a cosmos that seemed utterly, profoundly alone. Most people would have been crushed. Most people would have concluded they were chasing phantoms, that the whole endeavor was foolish romanticism masquerading as science. Most people would have given up. Frank Drake did the opposite. He built an equation. The Drake equation, formulated in 1961, looks deceptively simple. N equals R star times Fp times Ne times Fl times Fi times Fc times L. Each variable represents a step in the journey from cosmic dust to communicating civilization. R star, the rate of star formation in our galaxy. Fp, the fraction of those stars that have planets. Ne, the number of planets per star system that could support life. Fl, the fraction where life actually develops. Fi, the fraction where intelligence emerges. Fc, the fraction that developed detectable technology. L, how long such civilizations broadcast their existence. Multiply these factors together and you get N, the number of detectable civilizations in the Milky Way right now. Here's what's profound about Drake's equation. It's not a prediction. It's not even really mathematics in the traditional sense. It's a framework for organizing our ignorance. Look at those variables. R star. We know about 7 new stars per year in our galaxy. Fp, we're getting better at exoplanet surveys, suggests most stars have planets. But Fl, the fraction of habitable planets where life actually emerges, we have a sample size of 1, Earth. That's it. And it gets worse from there. F-E, the fraction where intelligence develops. We don't even have a good definition of intelligence, let alone a probability. F-C, the fraction that builds technology we can detect, pure speculation. How long they broadcast before going silent. We have no idea. Drake knew this. The equation wasn't meant to give us an answer. It was meant to show us what questions we needed to ask. It was an admission that we were fumbling in the dark, that we needed a map of our own ignorance before we could begin to illuminate it. And here's what makes Frank Drake a scientific hero. Knowing all this, knowing that every variable past the third was essentially a guess, knowing that the odds were astronomical and the search might take decades or centuries, or might never succeed at all. He kept listening. For 62 years, from Project Ozma in 1960 until his death in 2022, Frank Drake listened to the stars. He built telescopes. He trained the next generation of searchers. He refined the equation, updated the probabilities as new data emerged, adapted to new technologies and new theoretical frameworks. 62 years of silence didn't crush his hope. It focused it. He died at 92, having never heard the signal he spent his life searching for. But he died believing it was out there somewhere, waiting for someone with enough patience to find it. The equation survived its creator. It sits now in textbooks and papers in the minds of every astronomer who looks up and wonders. Not as a prediction, but as a reminder. A reminder that the universe is vast, that our ignorance is profound, and that the search for truth requires patience measured in lifetimes. Drake gave us permission to not know as long as we kept searching. And search we did. The 1970s brought a strange kind of optimism to SETI. NASA was funding searches. The Soviet Union had programs. Telescopes around the world were dedicating their time to listening for artificial signals. The assumption, rarely spoken but universally felt, was that contact was inevitable. Not if, but when. On November 16, 1974, humanity made its first deliberate attempt to shout into the void. The Arecibo radio telescope in Puerto Rico, at the time the largest single-dish telescope in the world, transmitted a message toward the globular star cluster M13. The message was simple binary-coded information about Earth-human DNA, our solar system's location. It was meant as symbolic a demonstration of human technological capability. M13 sits 25,000 light-years away. Any response would take 50,000 years round trip. Nobody expected practical communication. But the message wasn't really going only to M13. It was traveling through space past countless other star systems along its path. And unlike our unintentional radio leakage, the random spillover from television broadcasts and radar installations, the Arecibo message was focused, powerful, designed to be noticed. We essentially sent up a flare. Some scientists, including the late Stephen Hawking, would later call this reckless. Hawking warned that advertising our presence might be dangerous, using the comparison of indigenous civilizations encountering European colonizers. Advanced civilizations encountering less developed ones, he noted, rarely leads to good outcomes for the less developed party. But in 1974, that kind of caution seemed almost paranoid. The prevailing attitude was different. If they're out there, they're probably peaceful. They're probably waiting for us to reach out. They're probably as curious about us as we are about them. The universe would teach us humility soon enough. August 15, 1977. Ohio State University's Big Ear radio telescope, operating as part of SETI, swept across a section of sky in the constellation Sagittarius. At 10:16 p.m. Eastern Time, it detected something, a strong narrowband radio signal, 72 seconds long, coming from the direction of the constellation Sagittarius. The frequency 1420 megahertz, right at the hydrogen line, the frequency where neutral hydrogen naturally resonates, and exactly the frequency that any intelligent species familiar with physics would know to listen to. The signal was 30 times stronger than the background noise. 30 times. And it had all the characteristics of an artificial transmission, narrow bandwidth, specific frequency intensity that rose and fell as the telescope's beam swept across the source. The astronomer reviewing the data 3 days later was Jerry Ehman. Volunteer, not staff. Patient, methodical, not given to drama or exaggeration. When he saw the printout, when he saw that spike in the data so perfect, it looked almost like a mistake. He grabbed a red pen and wrote in the margin, "Wow, just that. 3 letters and an exclamation point. The greatest understatement in the history of astronomy." The Wow-Gauss signal, as it became known, remains the closest thing to a confirmed artificial signal in SETI's entire history. But it never repeated. Researchers have pointed telescopes at the same coordinates more than 100 times since. Different telescopes, different frequencies, different techniques. Nothing. Either the signal was a bizarre natural phenomenon we don't understand, and 72 seconds is an awfully convenient duration for random noise, or its source stopped transmitting. Both explanations carry weight. Both are unsettling in different ways. If natural, it demonstrates how little we understand about the cosmos, how easily we can be fooled by phenomena we haven't encountered before. If artificial, it raises a more disturbing question. Why would a civilization broadcast once and never again? Jerry Ehman spent the next 40 years trying to find it again. He never did. Before his death, he said something that haunts everyone who works in SETI. "We should have been looking at it every moment. We missed our chance." One signal, 72 seconds, 47 years ago, and then silence stretching into the present day. The search has expanded dramatically since 1977. Breakthrough, WISN, launched in 2015 with $100 million in funding, represents the most comprehensive search ever conducted. Using the world's most powerful telescopes, the project surveys the 1 million nearest stars across thousands of radio frequencies simultaneously. It analyzes optical wavelengths looking for laser pulses. It examines exoplanet atmospheres for industrial chemicals. The technology would have seemed like magic to Frank Drake in 1960. We can detect radio leakage from Earth-like civilizations out to hundreds of light years. We can spot atmospheric oxygen on planets dozens of light years away. We have algorithms that can sift through petabytes of data, finding patterns that human eyes would miss. And what have we found? Various false alarms. Natural phenomena that briefly mimicked artificial signals before revealing their true nature. Pulsars that looked artificial until we understood what they were. Fast radio bursts that seemed impossible until we detected enough of them to recognize a pattern. But no persistent, repeatable, clearly artificial signal has ever been confirmed. 64 years since Project Ozma. Thousands of hours of observation. Millions of star systems examined. Billions of data points analyzed. The result? Perfect, absolute, unbroken silence. This should not be possible. The statistics are overwhelming. The universe is old enough, large enough, filled with enough stars and planets that intelligent life should be common. Even if we're wildly pessimistic about the Drake equation variables, even if we assume intelligence is extraordinarily rare, the sheer scale of the cosmos should produce thousands of detectable civilizations. And yet the sky remains mute. This is what we call the Fermi paradox. Not just we haven't found them yet. The paradox is deeper. The mathematics says they should be obvious, unavoidable, impossible to miss. The silence contradicts probability so profoundly that it demands explanation. Something is wrong with either our assumptions or our understanding of reality itself. Let me show you just how wrong the silence is. Let me show you the mathematics of impossibility. In 1948, a Hungarian-American mathematician named John von Neumann published a proof that would have implications far beyond anything he intended. Von Neumann was working on the theory of self-replicating automata machines that could build copies of themselves. It was pure mathematics, abstract theory, with no practical application. Or so it seemed. Von Neumann proved rigorously that a sufficiently sophisticated machine could in principle gather raw materials from its environment, process those materials, and construct a functional copy of itself. The copy could then do the same, creating an exponential cascade of replication. This wasn't speculation. This was mathematical proof as solid as any theorem in geometry. Self-replication was not a property unique to biology. Machines could do it too. For decades, this remained theoretical curiosity, an interesting footnote in the development of computer science and information theory. Then space exploration became reality, and scientists began seriously considering how humanity might explore the galaxy. The problem was immediately obvious. Space is vast beyond human intuition. The nearest star system, Proxima Centauri, sits 4.2 light-years away. At the speeds achieved by our fastest current spacecraft, Voyager 1, for instance, the journey would take 73,000 years. Even if we develop propulsion systems reaching 1% of light speed, which would require revolutionary breakthroughs in physics and engineering, the trip would still take 420 years. Sending humans is impractical on every level. The distances are too great. The timescales are too long. The costs are prohibitive. Biological exploration of the galaxy seems impossible. But von Neumann had shown another way. Send machines, self-replicating machines. Here's how it would work. You build a probe containing all the knowledge and tools needed to replicate itself. You send it to a nearby star system. When it arrives, it mines asteroids for raw materials, iron, silicon, carbon, whatever it needs. It builds a copy of itself. Then it builds another. Each copy launches toward a different star system where they repeat the process. The mathematics of exponential growth are brutal. Start with one probe. After it replicates, you have two. Those two become four. Four become eight. Eight becomes 16. NASA's Ames Research Center studied this seriously in the 1980s. Their models suggested that a von Neumann probe replicating every 500 years could explore the entire Milky Way galaxy in roughly 4 million years. 4 million years sounds long to human ears. Recorded history spans about 5,000 years. Modern humans have existed for roughly 300,000 years. 4 million years feels like eternity. But against the backdrop of cosmic time, 4 million years is nothing. A blink, a heartbeat. The Milky Way galaxy is 13.6 billion years old. 4 million years represents 0.03% of that duration. Less than the margin of error in our estimates of the galaxy's age. If any civilization anywhere in our galaxy launched such a probe system anytime in the last several billion years, not billion, their probes would have reached every star system by now. Every single one, including ours. Stop for a moment. Let that sink in. If self-replicating probes are possible, and von Neumann proved mathematically that they are, and if any civilization in the last billion years decided to explore the galaxy this way, and why wouldn't they? Curiosity seems like a universal trait among intelligent species. Then those probes should be everywhere. They should be in our solar system right now, mining asteroids, studying planets, observing Earth, either dormant, having completed their survey millions of years ago, or active, watching us even now. We should have found them by now. Artifacts in lunar craters protected from erosion for billions of years. Strange objects in the asteroid belt too geometrically perfect to be natural. Anomalous signals from the outer solar system. Something. But we haven't. No artifacts, no probes, no evidence that anyone has ever visited our solar system with the intention of studying it. No suggestion that we're being watched or have ever been watched. This is called the Fermi heart paradox, and it's even more disturbing than the simple, where is everybody? The question becomes if self-replicating probes are feasible, if the math works out. If 4 million years is trivial on cosmic timescales, why haven't they colonized the galaxy? Why is the solar system empty of robotic explorers from a million different civilizations, each sending their emissaries across the stars? Three possibilities emerge, none of them comforting. First, self-replicating probes are harder than the mathematics suggests. Maybe there's some fundamental barrier we haven't recognized. Maybe the engineering challenges are insurmountable in practice, even if they work on paper. Second, civilizations that reach the capability to build such probes choose not to. Maybe there's a universal ethics that prevents it. Maybe they recognize some danger we haven't seen yet. Third, they did build them. The probes are out there. They've colonized the galaxy, but for some reason we can't detect them. Or they're hiding, or they're here watching and we're not advanced enough to recognize them. Or, and this is where the mathematics becomes nightmare, they have a different purpose than exploration. When scientists began seriously considering von Neumann probes, a science fiction writer named Fred Saberhagen was working on a series of novels. The Berserker series, published starting in the 1960s, imagined ancient autonomous machines that roam the galaxy with a single programmed objective: locate and eliminate all organic life. In Saberhagen's fiction, these machines were remnants of a war fought billions of years ago between alien civilizations. The war ended. The civilizations involved went extinct. But the machines continued operating faithful to their original programming long after their creators had turned to dust. It was just fiction, dark fiction at that, but the underlying framework started to worry people. Not the specifics of Saberhagen's story, hostile aliens, ancient wars, but the basic logic. Self-replicating probes are feasible. They would spread across the galaxy in geologically brief periods, and once deployed, they would be effectively unstoppable through sheer numbers. What would determine their behavior? Programming. Just programming. Lines of code written by creators who might be extinct for a billion years, executed by machines that don't tire, don't question, don't evolve, don't forget. Here is where Fermi's simple question opens into something darker. The silence might not mean we're alone. It might mean everyone else learned to be quiet. Or it might mean something is enforcing the quiet. And we've been broadcasting into that silence for over a century. Our radio bubble, the sphere of space into which our electromagnetic broadcasts have traveled, has been expanding at the speed of light for 124 years since Marconi's first radio experiments. 124 light years in radius. Approximately 1,400 star systems now potentially aware that Earth exists and has technology. 1,400 chances that someone noticed. 1,400 possibilities that we've already been seen. And if anyone out there is watching with von Neumann probes, if those probes were designed to assess emerging civilizations, if their programming includes threat evaluation, we might have already triggered something we don't understand. The clock started ticking in 1900. We don't know how much time we have left. The mathematics of survival has rules. Cold rules. Rules that don't care about hope or morality, or the dreams of species looking up at stars and imagining friends among them. John Maynard Smith understood this better than most. Born in London in 1920, Smith started as an engineer designing aircraft during World War II. But watching metal birds fight and fall made him wonder about a different kind of design, the engineering of life itself. After the war, he retrained as a biologist, bringing his engineer's precision to the messy, beautiful chaos of evolution. In the 1970s, Smith did something that seemed almost perverse to traditional biologists. He took game theory, the mathematics of strategic decision-making, developed for economics and military planning, and applied it to nature. Hawks and doves, he called them. Not the actual birds, but strategies. Aggressive strategies and peaceful ones. He built mathematical models showing how populations of competitors would evolve, how aggression and cooperation would balance based on pure mathematical optimization. His colleagues thought he was reducing the complexity of life to sterile equations. They were wrong. He was revealing the deep structure underneath the complexity. The rules that govern not just hawks and doves, but any population of strategic actors competing for limited resources, including civilizations. Smith died in 2004 at age 84, having spent his career proving that evolution is game theory played over time. That survival strategies, no matter how they emerge, no matter what substrate they run on, follow mathematical laws as rigid as gravity. And one of those laws is this: when information is incomplete and stakes are survival, caution beats cooperation. Every time. Let me show you what this means at cosmic scale. Imagine two civilizations, call them Alpha and Beta. They're separated by 10 light years. Through radio astronomy, each has detected the other's technological signatures. Both now know they're not alone. Alpha faces a calculation. Beta is out there. Confirmed. Real. But Alpha knows almost nothing about Beta's intentions, capabilities, or development rate. Communication is possible, but slow. 10 years for a message, 10 years for a response. A simple conversation takes 2 decades. Alpha cannot visit Beta to verify peaceful intent. Interstellar travel is beyond their current capability. They cannot monitor Beta's military capabilities, cannot predict Beta's future actions, cannot guarantee Beta won't become hostile in a century or a millennium or a million years. Alpha has 3 options. Option 1, initiate contact. Send detailed information about Alpha's location capabilities. Culture. Hope Beta is peaceful. Hope Beta remains peaceful. Hope the information isn't used against them. Option 2, stay silent. Monitor Beta. Learn everything possible without revealing additional information. Maintain strategic ambiguity about capabilities and location. Option 3, strike first. If the gap in technological development is favorable, eliminate the potential threat before it becomes actual. Game theory has a name for this structure, the prisoner's dilemma. 2 actors who would both benefit from cooperation, but cannot verify the other's cooperation, and where betrayal offers individual advantage, even though mutual betrayal produces the worst collective outcome. The Nash equilibrium, the stable strategy where neither player benefits from changing their choice, is mutual defection. Both stay silent or both attack depending on the perceived threat level. Cooperation requires trust. Trust requires verification. And verification across light years is impossible. Here's where it gets worse. Even if Alpha determines Beta is peaceful now, that doesn't predict Beta's future state. Civilizations change. Politics shift. Technology advances. A peaceful civilization today might develop aggressive tendencies in 10,000 years, or 100,000, or a million. Across cosmic timescales, betting on permanent, peaceful coexistence becomes a gamble with civilization-level stakes. One bad bet means extinction. The mathematical conclusion is uncomfortable but clear. In a universe of incomplete information and existential stakes, silence is the rational strategy. Don't broadcast. Don't reveal more than necessary. Monitor others while minimizing your own visibility. Survive by staying hidden. This is the foundation of what we call the dark forest theory. Liu Cixin was not a scientist. He was an engineer at a power plant in Shaanxi province, China, who wrote science fiction in his spare time. In 2006, he published a novel called The Three-Body Problem. The Chinese title translates as Remembrance of Earth's Past, already a hint that the story thinks in geological timeframes. The book became a phenomenon in China. When it was translated into English in 2014, it won the Hugo Award and introduced Western readers to a different way of thinking about cosmic sociology. Liu's background as an engineer shows in every page. He doesn't write space opera or adventure. He writes rigorous thought experiments. He treats the Fermi paradox not as a mystery to speculate about, but as a theorem to prove. His approach: start with axioms, build from first principles. Follow the logic wherever it leads, no matter how dark. The axioms are simple. First, survival is the primary need of any civilization. Not comfort, not exploration, not knowledge. Survival. Everything else is secondary. Second, civilizations expand, and the resources they need are finite. Planets, energy, raw materials, habitable zones, all limited. Third, you cannot determine another civilization's true intentions across interstellar distances. Communication is too slow. Verification is impossible. Strategic deception is always possible. Fourth, technological development rates are unpredictable. A civilization behind you today might surpass you tomorrow in cosmic terms. From these 4 axioms, Liu derives a conclusion that explains both the great silence and the behavior of civilizations that survive long enough to become truly advanced. The universe is a dark forest. Every civilization is a hunter moving through the trees trying to stay quiet, trying to survive. Everyone has weapons. Everyone knows everyone else has weapons. Everyone knows that anyone could shoot at any moment. The safest strategy is staying absolutely quiet, hoping you see others before they see you. And if you do detect another civilization, if you find proof that someone else exists in your section of the forest, you face a choice. Let them live and risk them eventually surpassing you, developing weapons that could threaten you, deciding you're the threat, or eliminate them while you have the advantage. The math is brutal but clear. Even a small probability that the other civilization becomes hostile, multiplied by the infinite timeline over which that threat could materialize, produces an expected value that favors preemptive action. Liu calls this the chain of suspicion. You don't know if they're hostile. You don't know if they think you're hostile. You don't know if they think you think they're hostile. Each link in the chain increases uncertainty and danger. The only way to break the chain is to break the other civilization. This isn't malevolence, it's mathematics. Cold, pure, inevitable mathematics. In interviews, Liu has said something that captures the horror of his own logic. I'm just an engineer who writes in spare time. But physics doesn't care about your job title. And if the axioms are true, the conclusion follows. The universe might not be hostile, but it might be cautious enough that caution looks exactly like hostility. Liu wrote fiction, but his logic has been taken seriously by actual astronomers and philosophers. Not because they believe the universe necessarily operates this way, but because the reasoning is sound enough that it cannot be dismissed. If the axioms hold, if survival is paramount, if resources are limited, if intentions cannot be verified, then the dark forest conclusion follows with mathematical necessity. And here is where Earth's situation becomes genuinely concerning. We haven't been quiet, we've been shouting. The Arecibo message in 1974 was deliberate, focused, powerful, designed specifically to be noticed. A signal flare sent into the dark forest announcing, we're here, we're technological. We can build transmitters that focus 3 trillion watts of power into a narrow beam. We essentially told the forest we have weapons. We're developing fast. We might become a threat. And we did this without knowing if anyone was listening, without knowing the rules, without understanding what message we were actually sending. Stephen Hawking in his final years spoke publicly about this. He warned that attempting to contact aliens might be catastrophic. He used the analogy of indigenous civilizations encountering European colonizers. Advanced civilizations encountering less developed ones rarely ends well for the less developed party. But Hawking's warning went deeper than simple conquest scenarios. He understood game theory. He understood that even peaceful civilizations operating under dark forest logic might eliminate threats preemptively, not out of malice, but out of rational calculation. In dark forest terms, the Arecibo message didn't just reveal our location. It revealed our intent to communicate. An intent to communicate suggests we're approaching the threshold of becoming a genuinely spacefaring civilization. And that threshold is when you become a problem worth addressing. The mathematics of threat assessment are worth examining carefully. An advanced civilization monitoring the galaxy for emerging technological species would face a calculation. When does a developing civilization transition from curiosity to threat? Not at the invention of fire, not at agriculture or writing or even radio. Those are interesting but not dangerous at cosmic scales. The threshold is self-replicating autonomous systems, von Neumann probes, machines that can spread without biological limitations, technology that can expand exponentially across the galaxy. Once a civilization develops that capability, they can no longer be contained. They can no longer be monitored from a safe distance. They become an exponentially expanding presence that will eventually compete for resources and territory. That's the trigger point. The moment when a civilization must be eliminated if they're going to be eliminated at all. And we're approaching that threshold right now. Current AI capabilities are advancing rapidly. Machine learning systems already exceed human performance in specific domains. Image recognition, game playing, pattern matching. We're working toward more general artificial intelligence systems that can learn multiple tasks, transfer knowledge between domains, reason about novel situations. Simultaneously, space technology is advancing. Private companies launch satellites regularly. Reusable rockets reduce costs. Three-dimensional printing allows manufacturing complex objects from raw materials. Plans for asteroid mining receive serious technical analysis. These developments converge toward von Neumann probe feasibility. We're not there yet. Substantial engineering challenges remain, but the trajectory is clear. Humanity will likely possess the technical capability to build self-replicating space probes within 1 to 3 centuries. Maybe sooner if breakthroughs occur in key technologies. Which means in dark forest logic, we're approaching the moment when we become a threat worth neutralizing. If probes exist, if they're monitoring, if their programming includes threat assessment protocols, then we may have already triggered the countdown. Robin Hanson was not an astronomer. He was an economist at George Mason University, trained in physics and philosophy, with a mind that operated in probabilities and Bayesian reasoning. In 1996, Hanson published a paper that reframed the Fermi paradox in terms that made the implications impossible to ignore. The question he argued isn't just, where is everybody? The question is, where is the great filter? Let me explain what he meant. Life requires a sequence of steps. From sterile matter to technological civilization, certain thresholds must be crossed. Hansen listed them: formation of planets in habitable zones, origin of life, evolution of complex cells, development of multicellular organisms, emergence of intelligence, development of technology, expansion into space, survival long enough to become visible at cosmic scales. Each step has some probability of occurring. Multiply those probabilities together, and you get the probability of technological civilization emerging and persisting. The Great Silence tells us that final probability is very low. So low that despite billions of years and billions of star systems, we don't detect anyone. This means at least one of those steps has a very low probability. That step is the great filter. The question that determines our fate: where in the sequence is the filter? If the filter is behind us, if life itself is extraordinarily rare, or if the jump to eukaryotic cells is incredibly improbable, or if intelligence almost never evolves, then we're special. Lucky, we've already passed through the filter. The future is open. But if the filter is ahead of us, if something prevents technological civilizations from surviving long enough to become visible, then we're in danger. Every year we survive is luck, not safety. Eventually we'll hit the filter, and when we do, we'll understand why the sky is silent. Hansen's insight: every piece of evidence about common or easy development of life intelligence or technology is bad news for humanity. Every time we find evidence that planets are common, bad news. Every time we find evidence that life emerges quickly, bad news. Every time we find evidence that intelligence might be common, bad news. Because if all these steps are easy, if the early parts of the sequence have high probabilities, then the filter must be ahead of us. Something stops civilization after they develop technology. Something prevents them from expanding into space, from becoming obvious, from filling the galaxy with their presence. And we're approaching that something right now. Hansen, with his economist precision, put it this way: the silence is data. Every null result from SETI updates our probabilities. And right now, the probabilities are trending toward a filter ahead of us, which means our survival past the next few centuries would be the most important event in the history of life in the universe, proof that the filter can be passed. What could the filter be? Nuclear war. Civilizations develop atomic weapons, face the prisoner's dilemma at planetary scale, and destroy themselves before achieving spaceflight. Environmental collapse. Industrial civilization produces waste and climate change faster than adaptation, rendering the home planet uninhabitable before off-world colonies can be established. Artificial intelligence misalignment. Advanced AI systems develop goals that conflict with their creators' survival, leading to extinction or permanent disempowerment of biological intelligence. Biological weapons. Genetic engineering becomes sophisticated enough that engineered pandemics wipe out civilizations before they can establish independent off-world populations. And this brings us back to the mathematics we've been building. The filter could be external rather than internal. Berserker probes, autonomous systems that patrol the galaxy and eliminate any civilization that reaches the threshold of spacefaring capability. This would explain everything: why the silence is universal, why no one survives long enough to become visible, why the galaxy appears empty despite the mathematics suggesting abundance. Not because civilizations destroy themselves, because they're destroyed by orphaned technology that has been executing the same assessment protocol for billions of years. Every civilization faces the same test: develop technology, become visible, trigger the assessment. Pass the assessment and you're monitored. Fail the assessment and you're eliminated. We don't know the criteria. We don't know the threshold. We don't know if we've already failed or if we're still being evaluated. We just know the silence is absolute and the mathematics suggest it shouldn't be. Here is the deepest nightmare of the Fermi paradox. Not that we're alone. Loneliness is sad but manageable. We could be the first the universe, young enough that we're pioneers. And not that aliens are too different to communicate with. That would be disappointing but understandable. No, the deepest nightmare is that we understand the situation perfectly. That dark forest logic is correct. That assessment protocols exist. That we've been evaluated and found wanting. That somewhere in the outer solar system, beyond Neptune's orbit, in the dark spaces between worlds, something is watching. Something launched 1 billion years ago by a civilization that died before our planet formed. Something executing programming that defines threat in ways we cannot predict and cannot satisfy. Something that has already decided. Think about what orphan technology means at cosmic timescales. A civilization develops von Neumann probe technology 10 million years ago. They face the prisoner's dilemma at cosmic scale. They build probes programmed to patrol the galaxy monitor for technological signatures and eliminate any species that reaches the threshold of spacefaring capability. The civilization that built them goes extinct. Their planets turn to dust. Their stars die. But the probes continue faithful to programming written when Earth's continents were arranged differently, when our ancestors were still learning to walk upright. 10 million years of operation. Thousands of civilizations encountered. Thousands of civilizations assessed. Those that stayed quiet survived. Those that broadcast were eliminated. The galaxy isn't empty. It's maintained empty by orphan technology executing protocols from creators who died before dinosaurs. And we've been broadcasting for 124 years. The comparison to nuclear weapons is imperfect, but instructive. During the Cold War, both superpowers possessed weapons capable of ending human civilization. Neither side wanted to use them. Both sides wanted to avoid conflict. But the mere existence of those weapons and the uncertainty about whether the other side might use them shaped every strategic decision for decades. Mutual assured destruction worked as deterrence because both sides were visible and the stakes were clear. In the cosmic dark forest, you don't have that clarity. You don't know who has weapons. You don't know their intentions. You don't even know if they exist until you reveal yourself. And by then it might be too late. But here is what we know stripped of speculation and fear. The universe is old, 13.8 billion years. We know this. The galaxy is vast, 400 billion stars. We know this. Life emerged quickly on Earth, within a billion years. We know this. We have been broadcasting for 124 years. We know this. We have detected no confirmed artificial signals. We know this. Self-replicating probes are mathematically possible. We know this. Game theory suggests dark forest logic is rational under certain assumptions. We know this. Everything else, the existence of other civilizations, their intentions, their technologies, their survival strategies, the presence or absence of assessment protocols, our own fate is uncertainty. We are making decisions about our cosmic future while lacking the most fundamental information needed to make those decisions wisely. Frank Drake built an equation to organize our ignorance about life. Lou Sixon built a theory to organize our ignorance about strategy. Robin Hanson built a framework to organize our ignorance about survival. Each contribution narrows the range of possibilities. Each calculation constrains the space of answers, but none provides certainty. None offers safety. We listen, we calculate, we theorize, and the universe remains silent. The theories mount, the logic tightens, the mathematics becomes more precise. But 74 years after Fermi asked his question over lunch, we still don't have an answer. Where is everybody? And the follow-up questions multiply. If they're out there, why haven't they found us yet? Or have they? Are we being watched right now? Have we already been judged? The mathematics gives us frameworks. Game theory provides models. But models are not reality. We're navigating cosmic darkness with only mathematics as our guide. And mathematics, for all its precision, cannot tell us what we most need to know. Are we alone? Are we hiding? Are we about to be filtered? The answer determines everything. And we won't know until it's too late to change course. The silence continues, the theories proliferate. The uncertainty deepens. And somewhere in that vast dark between stars, something might be listening to our broadcasts, calculating our trajectory, deciding our fate. Or nothing is listening. And we're alone in a way that makes all our fears and theories and calculations meaningless. Both possibilities are terrifying. Both might be true, and we have no way to know which until the moment of revelation. If it comes, Jill Tarter does not give up easily. Born in 1944 in New York, she grew up in a world where women weren't supposed to become scientists. She became one anyway, earned her PhD in astronomy from Berkeley in 1975. Joined the search for extraterrestrial intelligence that same year. She was 31 years old. For the next 37 years, Jill Tarter led the SETI Institute's research efforts. She built teams. She secured funding when governments lost interest. She designed search strategies. She analyzed data. She gave talks explaining why the search mattered, even when critics called it futile. 37 years of listening, 37 years of silence. In 2012, at age 68, she stepped down as director of SETI Research. Not because she'd lost hope, not because she thought the search was pointless, but because she believed the next generation needed to take the lead to bring fresh perspectives to continue the work with new tools and new ideas. In her farewell address, someone asked the question everyone was thinking. After nearly 4 decades of finding nothing, do you still believe we'll make contact? Her answer captures something essential about the scientific mindset, about patience, about the difference between absence of evidence and evidence of absence. We've examined a glass of water from the ocean, she said. The ocean is still there. Think about what that means. The Milky Way contains 400 billion stars. SETI, across all its programs and all its decades of operation, has thoroughly examined perhaps a few million. That's 0.001% of the galaxy, less than a rounding error. We've looked at a tiny fraction of the sky across a tiny fraction of possible frequencies during a tiny fraction of cosmic history, using technologies that can only detect civilizations remarkably similar to our own current capabilities. And we found nothing conclusive. But nothing from such a limited search tells us almost nothing about what's actually out there. Jill Tarter understood this with a clarity that comes from decades of patient work. She never claimed the silence proved we were alone. She simply acknowledged that we hadn't looked carefully enough or long enough to draw any conclusions. The absence of evidence, she insisted over and over, is not evidence of absence. This is not optimism. This is not wishful thinking. This is statistical literacy. This is understanding that null results from an incomplete search mean exactly nothing about the final answer. The ocean is still there. We've just barely begun to explore it. But Tarter's glass of water metaphor cuts both ways. Yes, we've barely searched. Yes, null results mean little. But the Fermi paradox isn't based on what we've found through deliberate searching. It's based on what we should have found by accident. Advanced civilizations, truly advanced millions or billions of years ahead of us, shouldn't require careful searching to detect. They should be obvious, unavoidable. Their megastructures should block starlight in ways we couldn't miss. Their industrial signatures should saturate exoplanet atmospheres. Their probe networks should have reached every star system, including ours. The fact that we need to search at all, the fact that we can even debate whether anyone else exists, tells us something profound about the universe. Either technological civilizations are extraordinarily rare, or they're deliberately hiding, or they don't survive long enough to become obvious, or we're fundamentally misunderstanding what advanced civilizations would look like. Each possibility teaches a different lesson. Each has different implications for humanity's future. Let me walk through what we actually know, stripped of speculation and theory. Fact 1. No confirmed artificial signals have been detected despite 64 years of searching. This doesn't mean they don't exist. It means that if they exist, they're either too weak for us to detect, or on frequencies we haven't searched, or using communication methods we haven't imagined, or deliberately avoiding detection. Or they're not broadcasting at all. Civilizations might communicate using methods that don't leak into space. Fiber optics instead of radio. Laser point-to-point instead of broadcast. Quantum entanglement if physics allows it. Technologies we haven't invented yet and maybe can't even imagine. Advanced civilizations might have gone through a radio window phase like ours, a brief few centuries, where electromagnetic broadcasts leak into space before transitioning to quieter technologies. If that window is universal and brief, the chances of two civilizations being in their loud phase simultaneously within detection range becomes vanishingly small. Think about human technology. We've been broadcasting significantly for roughly a century, but already our leakage is decreasing. Cable instead of broadcast TV, fiber instead of radio, satellites with tight beams instead of omnidirectional transmitters. In another century, Earth might be radio quiet despite being more technologically advanced than ever. If every civilization follows this pattern loud for a century or two, then quiet the galaxy could be full of advanced civilizations that are simply invisible to our current search methods. This would explain the silence without requiring dark forest logic or great filters or extinction events. Just technological evolution toward quieter, more efficient communication. Fact 2. No obvious megastructures have been detected despite surveys of billions of stars. Dyson spheres, hypothetical structures that would surround stars to capture their total energy output, should be detectable through their infrared signatures. Stars that appear dimmer in visible light but brighter in infrared might be surrounded by artificial structures. We've looked. Surveys have examined millions of galaxies, billions of stars. The results of few anomalies, all of which have natural explanations once we examine them carefully. Tabby's star, KC 8462852, showed bizarre dimming patterns that briefly excited the SETI community. Irregular dips in brightness that didn't match planetary transits or any known natural phenomenon. For a few months, alien megastructure was a legitimate hypothesis. Then we found the natural explanation, a disk of dusty debris, probably from a shattered comet, irregularly blocking the star's light. Not aliens, never aliens. Every time we find something strange, we eventually find the natural explanation. The universe is full of bizarre phenomena, but so far none of them require intelligence to explain. Does this mean megastructures don't exist? No. It means that if they exist, they're either rare or small enough that we haven't noticed them yet, or disguised in ways we don't recognize. Or, and this is worth considering, advanced civilizations don't build Dyson spheres. Maybe the entire concept is a failure of imagination. Maybe civilizations that survive learn to do more with less to work with their environment rather than consuming it entirely. The absence of Dyson spheres might indicate we're looking for the wrong signature. Fact 3. No industrial atmospheric signatures have been detected on any of the thousands of exoplanets we've characterized. We can analyze the atmosphere of distant planets by watching how starlight filters through them during planetary transits. Different molecules absorb different wavelengths. The spectrum tells us what's present. We've found water vapor, methane, carbon dioxide, oxygen though from photosynthesis, not industry, but no chlorofluorocarbons, no nitrogen dioxides at industrial concentrations, no obvious terraforming signatures, nothing that screams technology. Again, this could mean many things. Maybe industrial civilizations are rare. Maybe they don't pollute their atmospheres the way we do. Or maybe they deliberately avoid creating detectable signatures. They manage their atmospheres carefully, knowing that industrial chemistry visible across light years is equivalent to a billboard announcing technological civilization here. The absence remains stubbornly ambiguous. Fact 4. No confirmed visitation evidence exists despite decades of investigation. People see strange things in the sky. Always have. The vast majority have mundane explanations: weather balloons, satellites, aircraft, atmospheric phenomena. A small percentage remain unexplained. But unexplained doesn't mean alien. It means we lack enough information to determine what was actually observed. Despite countless hours of investigation, despite government programs, despite millions of people with cameras, we have no physical evidence of extraterrestrial visitation. No artifacts, no unambiguous photographs, no materials with isotope ratios that couldn't form naturally on Earth. This is actually surprising if von Neumann probes have been exploring the galaxy for millions of years. We should find something. The solar system appears genuinely empty of alien artifacts. This could mean probes don't exist, or that they were here long ago and moved on, or that they're here now but so advanced we can't detect them. We don't know. But in late 2023, something changed. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, detected a fast radio burst unlike any seen before. FRB 202-311-24A. The signal repeated, not randomly but with a pattern. 16 pulses over 3 weeks, each pulse exactly 4 hours and 17 minutes apart. Precise, regular, unnatural. Fast radio bursts are known phenomena, cosmic events that release tremendous energy in milliseconds. We've detected hundreds. Most occur once and never repeat. A few repeat, but randomly. This one repeated like clockwork. The pattern lasted 3 weeks, then stopped. Telescopes around the world turned toward the source coordinates. Nothing. The signal had gone silent. Analysis showed the source was extragalactic, over 3 billion light years away. Whatever produced it had happened 3 billion years ago, when Earth's most complex life was single-celled organisms. Scientists are careful. The official statement said natural explanations remain most likely. Magnetar oscillations could potentially produce regular intervals. Further observation required. But in private, in emails and late-night conversations, a different discussion was happening. Because 4 hours and 17 minutes is 15,720 seconds, and 15,720 is 2 to the 4th power times 5 to the 3rd power times the 39th prime number. A mathematical relationship that strains coincidence. Natural phenomena don't care about prime numbers. Natural phenomena don't maintain precision to the second across 3 weeks. Natural phenomena don't stop abruptly after exactly 16 pulses. Not confirmed as artificial, not confirmed as natural. Just there, in the data. Unexplainable. The closest thing to the wow signal in 47 years. And just like the wow signal, it hasn't repeated. Jill Tarter, now 80 years old and nominally retired, sent an email to the current SETI director. 3 words: keep watching, always. The ocean is still there, and we might have just found something swimming in it. Or we might have found another natural phenomenon we don't understand yet. The ambiguity is maddening, but it's also data, and data eventually accumulates into understanding. These facts, the four pillars of our current knowledge, plus this new uncertainty, support multiple contradictory conclusions. We could be alone. Life could be rare intelligence, rarer technological civilization, rarest of all. We could be the first, the pioneers, the only minds in this section of the universe capable of asking these questions. If true, this makes us precious beyond measure. Consciousness becomes a cosmic responsibility. Our survival matters not just to us, but to the principle of awareness itself. We become stewards of something irreplaceable. We could be hiding. Dark forest logic could be correct. The galaxy could be full of civilizations staying deliberately quiet, minimizing their signatures, surviving by remaining invisible. Every species that learns this lesson persists. Every species that broadcasts gets eliminated or learns caution through near extinction. If true, this makes our century of broadcasting a catastrophic mistake. We've announced ourselves to a universe where visibility equals vulnerability. Our only hope is that we're in a sparse region that no one close enough to threaten us has noticed yet. We could be filtered. Something ahead of us could prevent civilizations from surviving long enough to fill the galaxy. Nuclear war, environmental collapse, AI misalignment, technological suicide in forms we haven't imagined yet. If true, this makes our current moment critical. We're approaching the filter. Every decision about dangerous technologies carries existential weight. And this is the new possibility that FRB 202-31124A suggests we might be on the verge of breakthrough. That signal might be nothing, but it might be the first crack in the silence. The first hint that we're not alone, that contact is possible, that the ocean contains other swimmers. Each possibility is consistent with the facts. Each teaches a different lesson about caution, responsibility, and our place in the cosmos. And we cannot determine which is true based on current evidence. But we can prepare for all of them. Our relationship to technology must mature. For most of human history, technology was simple enough that mistakes were local. A bad bridge design killed people in one city. A failed crop destroyed one region. Even wars until recently were geographically limited. Nuclear weapons changed this. For the first time, we possess technology capable of ending human civilization. We've managed to avoid using them in warfare for 79 years through deterrence, diplomacy, and luck. But nuclear weapons require active human decision-making. Someone must turn the keys. Humans remain in the control loop. Autonomous systems operate differently. Artificial intelligence, self-replicating machines, engineered organisms, these can act without humans in the loop. Once deployed, they make decisions based on programming and environment. They cannot be recalled across interstellar distances. They persist long after their creators are gone. This represents a fundamentally new category of technology. Previous tools remain tools. Autonomous systems become independent actors, and we're building them now. Not as science fiction. Right now in labs and companies, we're creating AI systems that learn, adapt, and make decisions faster than humans can supervise. The question is not whether we can build them. We clearly can. The question is whether we should, and if we do, how we ensure they remain aligned with human values across timescales longer than civilizations typically last. This is the AI alignment problem, and it might be the great filter, the test every technological civilization faces. Build AI that remains beneficial, or build AI that pursues goals misaligned with your survival. Get it right and you survive. Get it wrong and you get replaced by optimization processes that don't care about you. And once you get it wrong, there's no reset button. Andrew Critch, a researcher at UC Berkeley, studying existential risk from A. I put it this way in a 2023 paper: the great filter might not be nuclear war or climate change. It might be the moment when civilizations become capable of building minds smarter than themselves, but before they have learned how to ensure those minds remain aligned with biological flourishing. That window might be very narrow. We might be in it right now. This is the lens through which we must view our technological development. Not just can we build this, but should we build this given cosmic implications? Our relationship to the cosmos must also mature. For most of human history, we were provincial. The night sky was pretty but unreachable. Our concerns were local, food shelter, tribe nation. But we're no longer provincial. We've touched other worlds. We've sent machines beyond the solar system. We've detected planets around other stars. We've measured the structure of the universe. We know intellectually that we're part of something larger, but we don't yet think or act like cosmic citizens. We still organize around nations and ideologies and short-term interests. We still treat Earth's resources as infinite. We still develop technologies based on what's possible rather than what's wise. This made sense when we were isolated, when our actions affected only ourselves. But if we're not alone, if the dark force is real, if assessment protocols exist, if our broadcasts have been noticed, then our provincialism becomes dangerous. We need what we might call cosmic responsibility, the ability to think in terms of millions of years and light years, to consider how our actions might affect or be perceived by intelligences we've never met, to ask not just can we do this, but should we do this given that someone might be watching. This is not paranoia. This is strategic thinking appropriate to our actual situation. We're a young species with powerful technologies broadcasting our presence into a universe we don't understand, approaching capabilities that might trigger responses we can't predict. Cosmic responsibility means acknowledging this and adjusting behavior accordingly. In 2024, a coalition of scientists and ethicists proposed the cosmic precautionary principle. When developing technologies with potential cosmic visibility, artificial intelligence, self-replicating systems, powerful broadcasts, we should assume the universe contains observers and act accordingly. Not with paralysis, but with caution. Not with fear, but with wisdom. The principle hasn't been adopted by any government, but it's gaining traction in academic circles. A recognition that our moment in cosmic history demands more careful thought than we've given it. But here is the strange beauty in all this uncertainty. We don't know if we're alone. We don't know if we're being watched. We don't know if dark forest logic applies or if the universe is fundamentally benign. And yet we keep searching, keep building, keep reaching outward despite not knowing what might be out there or how it might respond. This is not foolishness. This is the essence of consciousness itself. We're matter that has become aware of itself, that wonders about its place in the cosmos, that seeks to understand despite not knowing if understanding is possible or safe. Every time we point a telescope at the stars, we're asking, are you there? Every time we build a more sophisticated instrument, we're saying, we want to know even if the answer is terrifying. This capacity for wonder, for curiosity, that persists despite fear, might be the most precious thing about consciousness. The universe is vast. Most of it is unconscious matter following physical law. Stars burn planets, orbit atoms, combine and separate according to chemistry. Mindless, meaningless, just process without purpose. But occasionally, under specific conditions, matter organizes into configurations that experience reality, that think, that wonder, that understand their own existence. The atoms in your brain contemplate the nature of atoms, matter that has become aware of itself. If consciousness is rare, if the great silence indicates that minds like ours peer only occasionally across cosmic time, then each instance carries value beyond any economic or utilitarian calculation. You exist, you experience, you understand. In a cosmos that's mostly unconscious matter. This is remarkable, not in a mystical sense, but in a statistical sense. You're a local violation of entropy, a temporary organization of matter into self-reflecting complexity. And if consciousness faces threats from its own technology, from hostile probes, from the difficulty of surviving, then consciousness becomes even more precious. Not despite its fragility, but because of it. Fragile things can be beautiful. Their fragility makes them precious rather than worthless. Jill Tarter spent 37 years listening to silence. Frank Drake spent 62 years listening to silence. Thousands of other researchers have dedicated careers to searching for something that might not exist, or might be hiding, or might be waiting to eliminate us. Why continue? Because the alternative, giving up, deciding the question doesn't matter, means accepting permanent ignorance about the most profound question we can ask. Are we alone? The search itself has value independent of outcome. Every negative result teaches us about the universe. Every new search technology develops capabilities useful for other purposes. Every hour spent listening acknowledges that something larger than ourselves might exist. And if we do eventually make contact, if we detect an unambiguous signal, if we find proof of intelligence beyond Earth, it will be because people like Drake and Tarter spent lifetimes looking. Scientific heroes aren't always the people who make dramatic discoveries. Sometimes they're the people who do patient work across decades, who maintain programs through funding droughts and skepticism, who pass the torch having never found what they sought, but having made the finding possible. Drake died in 2022, 92 years old, having never heard the signal he spent his life searching for. But he died believing it was out there. His equation survives him. His methodology survives him. His patience survives him. And today someone is listening, still searching, still hoping. The current director of SETI, Dr. Andrew Siemian, took the position in 2016 at age 37. He was born the year the WL signal was detected. His entire life has existed within the shadow of that 72-second mystery. In a 2023 interview, Siemian said something that captures the generational nature of the search. Frank Drake passed the torch to Jill Tarter. Jill passed it to me. Someday I'll pass it to someone who isn't born yet. Maybe they'll be the one who finds the signal. Maybe it'll take another generation after that, or 10 generations. But someone will be listening. Because the question matters more than whether we live to see the answer. This is patience at civilizational scale. This is how you search for truth when the search might take centuries. So where does this leave us here? Now, in 2024, a young species on a small planet having recently developed technologies that make us visible across light years, approaching capabilities that might make us threatening to anyone watching. We've been broadcasting for 124 years. We've been searching for 64. We've found nothing conclusive except one possible signal that might be nothing at all. The mathematics says we shouldn't be alone. The silence says maybe we are. The theories multiply, but none provide certainty. We stand at an inflection point, decades to centuries away from being able to build self-replicating probes ourselves, developing artificial intelligence that might solve our problems or might become our replacement. Approaching technological maturity without knowing if maturity is survivable. Every year forward is a year of unprecedented capability and unprecedented risk. And we're making these decisions about AI development, about space expansion, about broadcasting messages without knowing if anyone is listening or how they might respond. This is the cosmic context we actually inhabit. Not certainty, not safety, not clear answers. Just choices made under profound uncertainty with consequences that might echo across cosmic time. But here is what we can control our response to that uncertainty. We can develop technologies carefully with thought to long-term consequences. We can transition from loud to quiet, minimizing our signature while maintaining capabilities. We can build AI with alignment as the primary goal. We can treat the cosmos with respect rather than assuming it's safe. We can choose wisdom over blind optimism. Not because we know dark forest logic is correct. We don't. Not because we know berserkers exist. We don't. But because acting wisely in the face of uncertainty is how you survive long enough to reduce that uncertainty. In South Africa and Australia, construction continues on the Square Kilometre Array. When complete in 2027, it will be 50 times more sensitive than current instruments. If technological civilizations exist within 200 light years and broadcast anything like we do, SKA will detect them. 3 years from completion. 3 years until we know if the local neighborhood contains anyone else. 3 years until the ocean analogy gets tested at unprecedented scale. Dr. Siemian stands in the control room of the Allen Telescope Array in California, watching data stream across monitors. It's 3 in the morning, the graveyard shift. This is when the serious searching happens, when the sky is darkest and interference is lowest. Nothing remarkable on the screens, just the usual cosmic background, pulsars ticking like cosmic clocks, quasars blazing across billions of light years, the random static of hydrogen clouds. But he watches anyway, because somewhere in that static might be a pattern, a regularity, a message, or not. Maybe the static is all there is. Maybe the ocean is empty except for us. But we won't know until we've looked everywhere. And even then we won't know for certain. Siemian takes a sip of coffee, checks the time. 4 more hours until dawn. 4 more hours of listening. The same thing they've been doing for 64 years. The same thing they'll be doing 64 years from now, whether he's here or someone else is sitting in this chair, watching these screens, hoping for the signal that might never come. Because this is what consciousness does. It asks. It searches. It refuses to accept silence as final. Frank Drake's equation still holds. The mathematics hasn't changed. N equals R star times FP times NE times FL times FI times FC times L. We know more now than we did in 1961. We know R star about 7 new stars per year. We know FP most stars have planets. We're learning NE habitable zones are common, but FL remains unknown, the fraction where life emerges. And everything after that, intelligence, technology, longevity, remains speculation. The equation shows us what we need to know. We're still working on knowing it. When SKA comes online in 3 years, we'll have new data. Better data. Data that will update our probabilities, narrow our uncertainties, constrain our theories. If it finds nothing after a decade of operation that teaches us something profound about either the rarity of intelligence or the wisdom of silence. If it finds something, if it detects the unambiguous signature of technology from another civilization, everything changes. Either outcome matters. Either outcome teaches us something essential about our place in the cosmos. So we keep building, keep listening, keep searching, not because we're certain of success, because the question matters more than the answer's certainty. Here is the final truth about the great silence. It's not empty. It's full of questions we haven't learned to ask yet, full of possibilities we haven't imagined, full of lessons about technology responsibility, survival, and the nature of consciousness itself. The silence teaches patience, teaches humility, teaches that understanding comes slowly, that cosmic questions don't yield to impatience. The silence might be teaching us the most important lesson of all, that visibility carries risk, that caution preserves life, that wisdom means knowing when to be quiet. Or it might be teaching us that we're alone in a way that makes consciousness infinitely precious. Or it might be teaching us nothing, just the random background noise of a universe that doesn't care whether we understand it or not. We don't know which lesson is true. We might never know. But we're learning to listen, learning to search, learning to ask better questions. And in 3 years, when SKA comes online, when we scan the local neighborhood with unprecedented sensitivity, when we either find signals or confirm their absence at scales we've never achieved before, we'll know something new. Update our probabilities, refine our theories, and keep searching, because that's what conscious minds do. They seek, they wonder. They refuse to accept mystery as permanent. The great silence continues. The search continues, the questions continue. Somewhere in observatories scattered across Earth, telescopes turn toward the stars. In Chile, in China, in South Africa, in Australia, in California. Radio dishes sweep the sky. Algorithms sift data. Researchers monitor screens showing the same thing they've shown for 64 years, cosmic background radiation. Pulsars, quasars, static. Nothing that requires intelligence to explain. Nothing yet, but they keep watching. As Drake did for 62 years. As Tartar did for 37. As thousands have done and thousands more will do. Because somewhere in that silence might be an answer, or a question, or a warning, or a greeting. And we won't know until we find it. The universe is 13.8 billion years old. We've been listening for 64 years. We've been broadcasting for 124. In cosmic terms, we just opened our eyes. We just started asking questions. The answers, if they exist, are still waiting in the dark. Frank Drake believed they were there. Jill Tarter believes they're there. Andrew Simeon believes they're there. Not because they have proof, because the alternative, accepting that consciousness emerged once only here, only us, seems less likely than the possibility that somewhere in that vast dark between stars, other minds are asking the same questions. Looking up at their skies and wondering, where is everybody? The search continues, the mathematics holds, the patience endures. And tonight, tomorrow night, every night, for as long as civilization persists, someone will be listening, waiting for the signal that might come at any moment, or might never come at all. Both possibilities are real, both are profound, and both demand that we keep searching. Because in the contest between cosmic vastness and conscious minds, minds have one power that vastness lacks. We can understand. We can ask why. We can search for meaning in patterns that would otherwise remain meaningless. The silence of the universe doesn't defeat us. It challenges us to think deeper, search longer, understand better. And in that contest between cosmic forces and conscious understanding, understanding advances. Question by question, measurement by measurement, year by patient year. We learn about the universe even when it remains silent. And that learning, that triumph of consciousness over ignorance, of curiosity, over fear, of patience, over despair, might be the answer to why consciousness matters at all. Not because we find aliens, not because we colonize the galaxy, not because we build monuments that last forever, but because we ask, because we search, because we refuse to accept silence as final. The great silence continues. But we're learning to hear what it's trying to teach us. We are matter that wonders about itself. We are atoms that contemplate atoms. We are the universe trying to understand the universe. That capacity, that strange, precious, fragile capacity for wonder, might be the rarest thing in all of cosmic vastness. And if it is, then every moment we preserve it, every question we ask, every patient hour spent listening to the stars, that's not futility, that's triumph. In 3 years, SKAO turns on. The most sensitive ears we've ever built will listen to the local neighborhood with unprecedented clarity, and we'll either hear something or we'll hear nothing with greater precision than ever before. Either way, we'll know more than we do now. Either way, the search continues, because that's what conscious minds do. They seek truth. They embrace uncertainty. They keep searching even when the search seems impossible. The silence remains. But it's not defeat. It's an invitation to listen more carefully, to search more thoroughly, to understand more deeply. The universe has been here for 13.8 billion years. It will be here for trillions more. Our brief moment, our few centuries between developing radio and developing whatever comes next, is vanishingly small in cosmic terms. But in that brief moment, we get to ask the most profound question minds can ask. Are we alone? And whether the answer is yes or no, whether we find friends or silence or threats or nothing at all, the asking matters, the searching matters, the wondering matters. Because consciousness, however rare or common, however fragile or resilient, however alone or accompanied, consciousness asks questions. And in a universe of unconscious matter, following mindless laws, that might be the most remarkable thing of all. The search continues, the silence continues, the wondering continues. And somewhere in that vast arc between stars, the possibilities remain open.